unofficial name was Water Train, based off of one activity that we did at the very beginning, where a number of us constructed essentially a train of boats for a completely separate naval engineering class.
Maybe you guys can introduce yourselves.
Oh, sure. I'm Dominic.
I'm Anthony.
I'm Timmy.
I'm Brett. Chase.
So essentially, as Professor Gilmore went over earlier, we used Rhino 3D along with the separate plugin Orchid to design our boat specifically. And he went over it a little bit as well, but for our purpose of research,
Why did we do what we did?
don't really know.
We were just able to pack, so we did what we did, but the total goal was to design a boat that had the least amount of resistance against it in calm water and wavy water, so I guess the most efficient boat in this sense. These are some terms to know. So the chine, that's where the side of the boat meets the bottom of the boat. It'll most likely be a very hard angle or a sharp angle, and that's where you can see a definite cut, usually where the water line is, or just below. The transom, that's the back of the boat. In our case, we used a flat transom, so it's like a hard cut off at the back. The hull, it's just the body of the boat. The bow, that's the front of the boat. The keel is the bottom of the boat. It runs from the bow to the transom. It goes underneath, and it's basically, if you were to cut the boat in half, the very bottom of that is the keel.
Spine.
Yeah, like the spine. The dead rise is the angle from the water up to the side of the boat, or up to where like the chine would be located. And then these are some photos. Can't read them on our computer, but that's some photos of where some stuff is. So this is the keel. That's the chine. The whole thing is the, what's it called? The whole thing is the hull. That's the transom, the bow, and then the dead rise is the angle from like the water level up to the chine.
So one of the things we were working on was generating lift with our boat. So a plane wing works by creating high pressure and low pressure areas, and that's what lifts it off the ground. But when you have a boat, it kind of does it backwards, and when you're moving fast, it actually pulls the boat down. Can you hit the button again? It pulls the boat down, and so one of the things we were working on was making all the edges really sharp, so that the water doesn't hug the sides and then pull it down further. So the sharper the angles you have, the less it gets pulled down.
And just going over again what would make a good boat, as Professor Orm said before, we want as flat a bottom as possible with as little dead rise for calm water in order to create more lift, as Jay said. However, this is terrible for wavy water, and in order to mitigate the accelerations, you need a steep dead rise angle in order to cut through the water. But in creating that steep dead rise angle, you diminish lift. And this here is a picture of our final boat design. As you can see, we have a width on the side, right where the chine is. This is to allow us to get a steeper dead rise while maintaining some flat surfaces in order to better optimize our boat for both calm water and wavy water performance. We have a midships dead rise of about 22 degrees and a transom dead rise of 18 degrees. And we have this variable dead rise because the majority of the encounter of waves is at the bow of the boat, and not much impact comes from the transom. So in order to further maximize lift, we reduce the angle at the back of the boat.
So this is the heat apparatus plus the weights that we need to add to make it an accurate reading for us. So the unknown springs take off about 17.5 pounds from the total weight we were using. The acceleration adds 0.28 pounds. The model itself weighs about 6.48 pounds. The drag balance, heat spacer, and pivot add about altogether 4.7 pounds. But our target weight was 11.5 pounds. So the weight we need to add was about 4.49 pounds.
So this is a video of our, oh wait, I can't click it, this is a video of the test with just calm water. Yeah, so, these are two graphs. The blue is what we predicted based off the numbers we got from, Orca 3D and Rhino. And as you can see, it's like not very accurate towards the end and pretty accurate in the beginning. The red is what came from that test there, and that was at 22 feet per second, right? Yeah. And this is the resistance, and this is the trim, which is the angle the boat rises out of the water. Yeah.
And then some observations for the calm water that we noted in various videos that we took at the different speeds, generally what was happening at each of the speed.
This is another video of the waves. While you're watching that, this graph, it's hard to see, I know that, but it shows, the two tests we ran in the waves. The first test is on the half, the other half is the second test. And each of these peaks is at a different, like, when it hits the wave, and it's hard to see, but this is the, I actually can't check because it's so hard to read, but I think it's the trim. I think this is the heave, and this is the, center of gravity. And it's showing, the changes in, how the waves affected those things.
And then again, just some other observations. One thing to note is that both of the tests were conducted at the same speed with the same waves. However, on the second test, through simply random chance, we encountered waves with a longer wavelength or time period between them, which resulted in slightly different pitch and center of gravity decelerations on the vessel itself. And then that's it.
So I have a question for you guys. So can you just give a quick summary of what your takeaways are, what you've kind of learned, or what your thoughts are over the course of the 2 weeks? I'm gonna put you on the spot.
One thing definitely of note is that the Orca 3D simulations were not as accurate as I thought they would be, as I think at the very end the real results were 180% of the expected results, which is interesting at the very least.
So that is a good observation. Often you're going to find that predictive tools are not perfect, but there was an issue with the spring. So you'll see when I present the results, I adjusted everybody's 2 higher speeds to account for the spring wasn't lifting. It had kind of a sticky point, if you will. So that when you should have been generating, an inch and a half, maybe inch and 3/4 worth of lift, you were only getting about an inch and a quarter. So it arbitrarily or artificially increased the resistance of those 2 speeds. So the predicted would have been better. That's the key takeaway, but not 180%. Anything else? Yes.
I learned that when you're designing a boat, it's important to find like a balance between different water conditions, especially when you're doing like different jobs. So that's when your boat's gonna